Okay, thanks, David.
Yeah, you're very welcome.
And welcome back, everyone. I'm glad to see many of you uh, came back. Um, okay, we will continue from last time, and also touch a little bit of in cryptographic applications, just to hopefully keep you more motivated to study the mathematics. Uh, yeah, what was that?
Hope you can hear me, guys. It's a bit noisy
Yeah.
here. Himatan. Yeah, let me see if I can enable the closed captions. Let's give it 2, 3 more minutes for more people to join before we can start.
Okay, it says please start the caption in the chat. I'm trying to find where that is. So I see closed caption here. Where is this? Looking for the setting now.
It's enabled, at least I can see it. Click on the three dots and go to the CC option, closed captions. I can see in the or like in the right, there's the chat on the left, and there's the CC option.
Sorry, I didn't really hear that. You said on the chat on the left, I see there's caption and it says translate to original and English. Is that what is just keep that open? Is that good? Maybe it's good now. Okay. Harvey said it's good to go.
It's all right.
Okay, cool.
So like people can individually, yeah, like people can individually choose to see the closed captions in the left box. Yeah.
Gotcha. Okay.
Okay, so we can start.
Yeah, should be good.
All right.
Yeah,
So
go ahead. Thank you so much. Yeah.
okay, so I remind you that we're doing some mathematics that is quite involved, and I want to encourage you to ask questions. I mean, even if it's simple questions, you can ask during the session. I like to have as many questions as possible. So even if you just want to make me happy, just ask questions. And last time, we talked about groups, and a group is basically a set with a binary operation and a neutral element satisfying some axioms. And we also talked about fields. And the main example we gave is you take a prime P, and you look at what is denoted as Fp, which is all the numbers which can be obtained as remainders modulo P. And on this set, you have addition modulo P. and multiplication modulo P. The neutral element with respect to addition is 0. And the neutral element with respect to multiplication is 1. And in the questions that that happened at the end of the session, somebody asked why should we care about this FP? And I began to give an answer, but I want to extend the answer now. So the main theorem that leads to this application is that if you take FP and you remove the 0 element, right? So you have 1 up to P minus 1. And you consider this operation multiplication modulo P. Then by the axioms of a field, this is an abelian group. But the theorem tells you that this is not just any abelian group, but rather a cyclic abelian group. And what does it mean? It means that there exists at least one generator in this set. I mean, one number between 1 and P minus 1, such that FP star can be described as all the possible powers of the generator. So G to the 0, which is by convention 1, G, or G to the 1, G squared, and so on until G to the P minus 1. Okay, sorry, P minus 2. So you see, we have P minus 1 elements here, and all of them are some power of P. So, or in other words, for any X in FP star, there exists some K between 0 and P minus 2, such that X is G to the power of K. Now, this leads us to what is called the discrete logarithm problem. The problem itself, I will state it without any explicit parameters. That is, if P and G are known, this is usually referred to in cryptography as public. All the people involved in this question can know P and G, and X is chosen randomly from FP star, then it is hard to find K as before, such that X is G to the K. And the reason it is called discrete logarithm problem is because you you know that x is equal to g to the k for some k. So if you had like a log on basis of g, and you could apply it, then it would be equal to k. So you could compute k if you had some kind of a hypothetical log on basis g function. Now, what does it mean hard? Hard, it means that it's hard relative to the size of p. And usually we measure the size of p in a number of digits. Number of digits is almost the same as number of bits. You know, there is some factor because we count usually on a decimal basis and not on a binary basis, but up to a small factor they are the same. So hard here really refers to or relative to the length of bit, let's say bit length of p. And it is common assumption. This is what is called the hardness assumption in cryptography, to say, for example, if a p is say has 2048 digits, then a DLP is infeasible. Even with a supercomputer, even with several hundreds of years or something like that. On the other hand, if you give me G and K, of course, and of course P, then it is computationally feasible to compute G to the K. G to the K mod P, right? Because we are in a field in a field FP, so we need G to the K mod P in order to go back to the field, or to the field without the zero element. So this is a classical example of a one-way function. I mean, if you give me G and you give me K, I can calculate. It may take some time, but it is definitely feasible even on a regular computer to compute G to the K for such a big prime number P. But after I give you the result, it's very, very hard. It's in fact infeasible to come up with the K that made this element G to the K or X. And under this hardness assumption, we have a cryptographic protocol, and this is called Diffie-Hellman key exchange. So before I describe it, I just want to say, I mean, cryptography is not just about sending secret messages. It is maybe the study of a wide variety of what is called primitives that preserve a privacy in some sense, but this is a loose definition, and there are many different kind of cryptographic protocols that have nothing to do with sending a secret message. Nevertheless, this Diffie-Hellman key exchange is a primitive towards being able to send a secret message. And the problem is as follows. So you have Alice and Bob living in two parts of the world, and they can only communicate through the internet. And they want to agree on a secret. As this secret is a secret key. Once they have a secret key they can agree on, then they can use another protocol to send encrypted messages to each other. But first they need to agree on a secret. And since they can only communicate within the internet, they must assume that everybody can listen to the communication. So they need to. So Diffie-Hellman key exchange protocol is a way for Alice and Bob to agree on a common secret by means of public communication. And the way it goes is very easy. So Alice chooses a secret, or sorry, before. So they need to agree before they start the protocol. Alice and Bob by public communication agree on prime P with say 2048 digits, and a generator for a FP star, generator G, i.e. G is some number between 1 and P minus 1, and G generates by, if you take powers of G modulo P, you get the entire FP star. These two things, I mean, choosing P and then choosing such a generator are computationally feasible problems. Choosing P, like is this, you probably all of you or most of you know how to do it efficiently. Choosing G is slightly more involved, but it's not a big deal. And they had to do it publicly. So they, it could be that Alice chose P and G and send it to Bob, and Bob simply checks that G is indeed a generator, that P is indeed a prime, and G is indeed a generator for FP star. But anyone who is listening to the communication can also see it. Okay, so these are the public parameters. And now the protocol begins. So Alice chooses secret S Alice. S Alice is a number between well, it's just a number between 1 and P minus 2. Or in fact, 0 and P minus 2 at random. So the notation here, the typical notation is that S Alice, the secret that Alice chooses, is taken at uniformly at random from a 0 up to p minus 2. And then also Bob does the same. Bob, he chooses the SB uniformly at random from 0 up to p minus 2. So this is this is Alice, let's say, and this is Bob. And we said that the first thing is that Alice takes a secret. How do we call it? Let's call this group, I call it big S. And Bob takes a secret at random from the set of secrets S. And then, because they agreed on a generator, Alice can send to Bob, we can call it X Alice, is, G to the S Alice modulo P. So Alice computes G to the SA modulo P. This is considered feasible, and sends the result sends to Bob, and we call this result X Alice. And Bob does the same. He has the secret that he chose at random, and he computes X Bob, which is G to the S Bob modulo P, and he sends it to Alice. So after the 2 rounds, Bob has XA and also SB, and Alice has XB and also SA. And the common secret is G to the XA times XB. How do they compute it? Well, Alice has X to the B, which is presumably, if Bob was honest, it is G to the SB. But Alice also has S Alice, so she can take X Bob and raise it to the power of S Alice. And this is by definition G to the SB to the SA mod P, but this by the axioms of mod P multiplication, this is the same as G to the SA times SB. Oh, I miswrote here. I apologize. The common secret is G to the SA times SB. Okay, so you see, Alice can compute the common secret with the information she has, and Bob can also compute the common secret because he has X Alice, and he can raise it to the power of S Bob, and this is G to the S Alice to the power of S Bob, and this is also G to the SA times SB. Now, what happened? Now, what about the security? So we assume that the discrete logarithm problem at this size of the prime is hard. So an eavesdropper, let's say, This is Eve. She's an eavesdropper, and she can see XA, but she cannot find out what is SA, even though she knows what is a G and P. And she can also see what is XB, but she cannot figure out what is SB, because again, she cannot solve the discrete logarithm problem. Now you may say, okay, but if she has XA and XB, she can multiply XA and XB. But if she multiplies XA and XB, what she gets is G to the power of SA times G to the power of SB, which is G to the power of SA plus SB. And everything here is mod P. So an eavesdropper can listen to the communication and calculate this quantity, G to the SA plus SB, but it cannot find out what is G to the SA times SB. And Alice and Bob, each of them has the information to calculate SA and SB. So that is considered the common secret. Questions? I see there is a bunch.
Yes, there were some answers in the chat already.
Yeah.
I think you. Yeah.
How can we find out if G is a generator? Yeah, so I didn't say it, but one way, I mean, you factor G to a product of primes. Let's put it in green here. G is just some number between 1 and P minus 1. So you can factor it to a product of primes. Let's say pi I equals 1 up to L. Okay? And then you check that G to the P divide P minus 1 divided by Pi is not equal to 1 modulo P for each I. And if you have that, then you know that G is a generator. So this is there is an algorithm that does it for you. Again, there's certain ways to make it a bit more efficient, but generally speaking, it is efficient. What else? No, that's not true that any point is a generator, because cyclic group is not always generated by any element. I mean, take, for example, integers modulo 4, it is not generated by the element 2. You do 2 plus 2 is 4, which is 0, and that's it. Any number of times you add 2 to itself, you cannot get to 3 modulo 4. In a field with P equals 7, G equals 2, doesn't work to generate the whole field. I don't understand. Is there any size constraint on G? The size constraint on G is basically the size constraint on the prime number, right? G is of size P minus 1. Yeah, and if you take P to be too small, then of course, then the discrete logarithm problem is not that hard. How does Diffie-Hellman works in an elliptic curve group? That's out of scope for now. But I very much hope to get to elliptic curves in this series of lectures, and we can discuss it then. Okay, So I hope you're motivated a bit more now to see that the mathematics we do has a very practical application in the cryptographic world, and this of course should be also the motivation when we start talking about curves and so on. But I would like to keep it as simple as possible for now. So the definition I want to talk about is now, so if you have a field, then the characteristic of the field, let's say a finite field, the characteristic of F is the minimal number such that the minimal number C, such that 1F plus itself C times is equal to 0. And the stress here is on the minimal. I mean, there must be some number. Just a second. I'll be back soon. So you see, obviously, if you have a finite field, then a 1 plus 1 has to be different than 1. And 1 plus 1 plus 1 has to be different than 1 and 1 plus 1. And so there is only finitely many possibilities that you can cover in the field. So at some point, you have to have a number of ones that you add to itself and gives you 0. That's the, let's say, the heuristic. And if F is infinite, we set that the characteristic of F is infinity. So, for example, the real numbers are considered to have infinite characteristic. And the first proposition, maybe observation, is for finite F, char F is always prime. Let's call it P. And what is the reason? Otherwise, char F, if the characteristic of F is not a prime, then it is, let's say, a product of two integers, K and L, with K and L bigger than 1. Then I do 1 plus 1 K times. and 1 plus 1 L times. And this is, if you use the distributive law, which is an axiom of a field, this is 1 plus 1 K times L times. Which is, we assume this is the characteristic. So it is equal to 0. But on the other hand, these two numbers are not 0. I mean, K cannot be 0, and L cannot, I mean, maybe we call it K sub F. This is this number, and this number is L sub F. When you add the unit element of the field L times, each of these numbers cannot be 0, because in a field, if a product of two elements is 0, at least one of them has to be 0. But Kf cannot be 0 because it will contradict the minimality of characteristic. Remember, characteristic, maybe I can write P here, is the minimal number, such that if you add 1 to itself this number of times, you get 0. And if K is already 0, then since K is smaller than P, then it contradicts the minimality of the characteristic. So here we say and Kf and Lf are different from 0 by a minimality of the characteristic. So that's a contradiction. So this, if we assume towards contradiction that the characteristic of the field is a product of two, a non-trivial product of integers, then we get a contradiction. So this means the characteristic of F is always, the characteristic of a finite field is always a prime number. And we know that for any prime number, we have the prime field Fp. But the question is whether there are others. Can there be other fields of characteristic P that are not exactly Fp, or not exactly Fp even up to isomorphism, right? We didn't define isomorphism of fields, but it's exactly analogous to isomorphism of groups. It's like if the addition and multiplication tables of the two fields are the same up to a change of notation, up to a change of names. So here's an example. I take we will call it now GF4. GF4 as a set, it has 4 elements: 0, 1, 2, 3. And the addition table of GF4 is the same as integers modulo 4. Okay, so 0, 1, 2, 3, 0, 1, 2, 3. If you want to do 2 plus 2, that's 0. And the multiplication table is a bit more tricky. Well, you multiply everything with 0, anything with 0, you get 0. You multiply anything that is not 0 with 1, you get the same. And now for the rest, it's 0 to 1. Okay, that's multiplication. And as an exercise, you can check that this is a field. I mean, to see, well, obviously, since integers modulo 4 is an abelian group, so the addition of this field is fine. If you want to find the multiplicative inverse, which is usually the problem, so multiplicative inverse of 1 is 1. Multiplicative inverse of 2 is I need to multiply 2. Wait. Yes, something is off for some reason. I think I copied it wrongly from somewhere. Now this. Let me just quickly Google it. Yeah. So 2. Oh yeah. So this needs to be 1 here. This needs to be 2. Yes. I'm sorry. I had a typo in my notes. But you see, so if you want the multiplicative inverse of 2 is 3, but the multiplicative inverse of 3 is 2. And observe that this is not multiplication modulo 4, because I take, for example, 2 times 3. This is 6 modulo 4. It should have been 2. So this the multiplication table here is not modulo 4. Somebody thought about it carefully, and you can see that this is a field. What is the characteristic of this field? Characteristic of this field is the minimal number such that 1 plus 1 is equal to 0. And since 1 plus 1 is equal to sorry, here, I apologize.
Hello.
Yes.
Like 2 into 3 is equal to 6 and 6 modulo 2 is equal to 2, but you put 1 in multiplication table.
I didn't say the multiplication is I didn't say the multiplication is modulo 4. I simply wrote a multiplication table. Let me write
this is wrong. This is the wrong. Your multiplication table is wrong.
It could be because I just copied it from somewhere, and I could have done a mistake, but let me double check. Yeah, let me double check this. No, I think Okay, so what we have here as the addition table. I mean, obviously, this is 0, 1, 2, 3. This is 0, 1, 2, 3. And now this is 1, 1, 0, 3, 2. And 2, yes, 2, 3, 0, 1, 2, 3, 0, 1. And here 3, 2, 1, 0. Okay, so let me double check the multiplication because you say, but I think the multiplication should be okay now. So what was that? Of course, 0, 0, 0. 0, 1, 2, 3. Yeah. 0, 2. 0, 2, 3 here. Yeah. 0, 2, 3, 1, and then 0, 3, 1, 2. Yeah. So it should be okay now. I apologize for this, but yes. Yes.
Why 2 into 2 is equal to 3?
There is no why. I present to you addition table and multiplication table. It's a free country, right? All I have to do is show you that the axioms of a field are satisfied. There is no why. The question why in definitions is, I mean, of course, now if you ask kind of how did I come up with it, okay, it's a different question. In this capacity, in this size, you can imagine that I just tried all the options. It's not so many options, and I stumbled upon addition and multiplication tables like so, and I checked, and the axioms are satisfied. Okay, and you can check. We checked by hand multiplicative inverse, and observe that the characteristic of the field is 2. Characteristic of GF4 is equal to 2. Okay, so we have a field of characteristic 2 that has 4 elements. I mean, obviously, it cannot have a characteristic 4 because we know that the characteristic of a field has to be a prime number. But on the other hand, so far we only knew about fields of characteristic 2 that have 2 elements, and now we see a field with 4 elements. So this should drive the curiosity to find out how can we construct new fields of characteristic P. Any other questions? Okay, so polynomials. This is now a detour, but it's an important detour even in its own right, even for many other applications. You need to know stuff about polynomials. So let F be a field. A polynomial over F is a formal expression let's write it like this. F x equals f0 plus f1 x plus f n x to the n, where the fi, so f0 up to fn, are elements in the field, and let's say by convention we assume that if we write it like this, then fn, the last one, is non-zero, because otherwise we can just omit it, and n is called the degree. Well, let me simply write it like this: a degree of f. The collection of all polynomials over f is denoted as a f. I mean, if you take variable small x, then it's denoted as f with a square brackets x, and f with square brackets x and less equal to n is all polynomials of degree less or equal to n. And here, let me just introduce one last type of writing. Instead of writing this long expression, we can write a sum I equals 0 up to n fi x to the I. Okay, so that's a polynomial. What does it mean formal? Formal means that two polynomials, f and g, let's say f is sum fi x to the I equals 0 up to n, g sum gi x, or maybe say gj x to the j equals 0 up to k, are equal if and only if n is equal to k, so they have the same degree, and for every I between 0 and n, fi is equal to gi. Okay, so formality here really refers to the notion of equality between two polynomials, and maybe the biggest warning that you should have with regard to polynomials, a polynomial is not the same as a function. Let's say f bar from the field to itself. Even though every polynomial, so every f gives rise or induces a unique function that we, by abuse of notation, many people denote it as still as f, but here let me distinguish it and call it f bar. F bar, it takes an element a, plug it in to the polynomial instead of the formal variable x, and calculate what you have in the expression and get some element in f. But not conversely. I mean, for example, f is equal to the prime field f2, which is just two elements, 0 and 1. The number of functions between f2 and f2 is there are only 4 possible functions. But there are many, many, many more polynomials. In fact, there are infinitely many polynomials over f2, because you can always take x to the n, where n is some number. So this is an important distinction. A polynomial can induce a function by substitution, but it's not the same as a function, and it's not the same exactly because of this this formality property. Now we have operations, natural operations on polynomials. One is addition. You give me let's say f and g, then of course it's like you add expressions that you had in whatever equations in the high school. I mean the sum of f and g, or what is called so add. Let's say for simplicity, maybe we do it m and n. And let's say that m is less or equal to n, then fx plus gx is simply a sum up to the smaller value. So let's say k is equal to 0 up to m, fk plus gk, x to the k, plus and the last part is only g, so plus sum from k equals to n plus 1 up to n, gk x to the k. Okay, and multiply, it's a bit more the formula is a bit more involved. I can write it down just for you to look it up later on, but of course intuitively it should be very clear. So fx times gx is going to be equal to sum ck x to the k equals 0 up to m plus n, and ck in itself has a bit of a convoluted formula. It's like this AI, not AI, Fi Bj, where I runs up to m, and j runs up to n, and I plus j is equal to k. Okay, but of course you can just take, take a polynomial x squared plus 1. If you want to multiply it by x cube plus 2x plus 2x plus 2, well, I mean, you just open the brackets and you get some polynomial expression. Okay, and then there is another operation, but I think that one is better to save for after the break. So maybe it's time to take some questions, and then 10 minutes break. Okay, so maybe before I introduce the next operation, well, let's do an example. So the next operation is long division. So I give you two polynomials. Let's say f is equal to the real numbers, and you want to divide 6x cubed minus 2x squared plus x plus 3. This we call f, by x squared minus x plus 1. This I call g. But like integers, sometimes polynomials just don't divide each other. So we want to do a division with a remainder. What do? We take the leading guy here, and we divide it by the leading guy here. What we get is 6x. So 6x is 6x cubed divided by x squared. We put it here. This is a part of the result. And then I take this 6x, I multiply it by this guy, x squared minus x plus 1. I get 6x cubed minus 6x squared plus 6x. And I subtract the result from the polynomial f. What do I get? I get the leading coefficient of f disappears. This is by design, right? And so I get minus 2x squared minus 6x squared. That's 4x squared minus 5x plus 3. And now again, I take the leading coefficient here, and I divide it by the leading coefficient here. The leading monomial, I should say. Well, what do I get? I mean, 4x squared divided by x squared is 4. So I put plus 4, which is 4x squared divided by x squared. Okay, and then I take this 4 and I multiply the polynomial g by 4. So this is 4 times x squared minus x plus 1. And the result is 4x squared minus 4x plus 1. And I subtract. Again, the leading coefficient disappears by design. So this is minus 5x minus 4x. This is minus x. And then 3 minus 1 is 2. Here it should have been 4. So 3 minus 4 is minus 1. And what I claim, and you can check, let's call this guy the quotient, qx, and we call this guy the remainder, rx. And you can check that f is equal to g times q plus r. And obviously, the degree of r is strictly smaller than the degree of g. So this is my stopping condition. I mean, if the degree of r would be a greater or equal than the degree of g, then I could do the same trick that I did with the green and the yellow all over again. I get rid of the leading, the highest monomial. And so, so you see, and this is more generally true. The theorem is for any f and g in f x. Note that I write for simplicity, I omit the variable x when I write f and g. This is a matter of taste, but it is a conventional writing. And I hope you will see later on that it's in some cases it's more intuitive to do it this way, to write it this way. For any polynomials f and g, such that the degree of g is smaller or equal than the degree of f, there exist unique polynomials q and r. Unique is always with respect to some condition. So satisfying the property, the two properties. One is that f is equal to q times r. Q times g plus r. And two is that the degree of r is strictly smaller than the degree of g. Okay, and sometimes you write f, many times in programming you do this this notation, f divided by g with remainder. So this is the remainder of the entire operation. Any questions about this long division? Okay, so the slogan here, maybe, well, the slogan is that polynomials, especially over finite fields, are like integers. And we will expand this analogy, but this is an informal statement. I mean, unlike stuff where we make a precise statement and we have a proof, this is an informal statement that is supposed to give you an intuition of how we proceed in various construction we will see, and don't dismiss this analogy so quickly. I think it is very, very helpful to think also in intuitive terms like this. So, well, I mean, one justification for this analogy is that we have long division. I mean, we have addition, we have multiplication, and we have long division. That's pretty similar already to integers. And another thing we have is a notion of prime polynomials. What is a prime polynomial? A polynomial f in variable x over a field big F is prime if it cannot be written as f is equal to, let's say, g times h, with g and h polynomials, let's say, non-constant. Because of course, I mean, if you take the leading coefficient of f, let's say f is 3x plus 3, then of course I can write f as 3 times x plus 3. That's not a, or it doesn't even have to be 3 here. It can be 4, for example, and then I can write f as 3 times x plus 3, sorry, 4 over 3. Okay, so but that's not an interesting factorization, because you can always do that. But if you can write f as a product of two non-constant polynomials, we call f a prime polynomial. Okay, so this is another piece of the analogy puzzle. Now, maybe an important corollary of this theorem star that it tells you that you can always do long division is what is called well, so if f is a polynomial over a field and a in f a root, sometimes it's called a zero of f, i.e. f, if you substitute a in f, then you get the zero element in the field. Yeah, this is a root. Then f, or there exist polynomial f bar in polynomials over f with variable x, such that f is x minus a times f bar of x. Why? Proof. Do a long division of f with x minus a. Now, if you do long division, this is, by definition, there is always some remainder, Rx. Okay? So I can write f, let's say fx is equal to x minus a times the quotient qx plus r of x. And the degree of r has to be smaller than the degree of the polynomial I'm dividing by. So it has to be smaller than the degree of x minus a. But the degree of x minus a is 1. That is, the degree of r has to be 0. So r is some constant polynomial, where c is an element in the field. Now I substitute a in this equation. F of a is equal to 0, right? And if I substitute on the right hand side, I get that this is r of a, because the first summand vanishes. So I get that r of a is equal to 0, but r is a constant polynomial, so c is equal to 0. And the corollary of the corollary a polynomial f of degree n can have at most n different roots or zeros. Why? Well, I mean, if a1 is a root, then I can write f of x equals x minus a1 times, let's call it well, whatever, f1 of x. And if a2 is a root, then, well, obviously, if I plug in, if a2 is different than a1, I plug it into x minus a1, it's not going to vanish. So it means that a2 has to be a root of f1. That means that fx is equal to x minus a1 times x minus a2 times some f2, and so on. And I can only do it n times, because the degree of f is n, and these guys can only, I mean, when they multiply, they can only reach up to x to the n. Is this clear? This is an important fact about polynomials. Okay, so we defined before this little detour, we defined what is a prime polynomial. Observe, any polynomial can be factored to a product of primes. Why? it's exactly the same algorithm, if you will, that you do for integers. I mean, you take an integer. How do you know that an integer can be written as a product of primes? You look at the first prime, 2. If 2 divides this integer, then you do the integer. You start with an integer, you check whether it is divisible by 2. If it is divisible by 2, you take n over 2, and you continue with the next prime, 3, and so on. And if not, you continue, you take n, and you ask whether n is divisible by 3. And since so there are only finitely many primes that are smaller than n, of course, it could be that 2 divides n by several times. So you check whether 2 divides n until it doesn't, and you check for all the primes smaller than n, and eventually you get a factorization of n to the product of primes. When you deal with polynomials over finite fields, if you give me a polynomial of degree n, there are only finitely many polynomials of degree less than n, or less than equal than n, that can be prime. I check whether this polynomial is divisible by each of these guys, and eventually I get to a product of primes expressing the original polynomial. Okay, so this is again an extension of the analogy. And now I want to use the analogy. So remember, how did we build the field of the prime field FP? What we did is we took integers, and we took integers modulo p, where we did integers modulo p is really, we took all the possible remainders of integers that are divided by p. I mean, all the mod p remainders. This is 0 up to p minus 1. Okay, these remainders. And on this set, we defined addition modulo the prime and multiplication modulo the prime, and we proved that this is for a prime number, that this is indeed a field. So now I'm going to do the same, but for polynomials. I take, so let phi, this is like our substitution for the prime. Be a prime polynomial. Let's say over a finite field. I can even simplify over. Well, okay, let's do it maybe over a finite field, and then this is valid over any field, but maybe easier to see it this way. Now I take I'll do this. So we said that polynomials with variable x, this is like the integers, right? And phi is like the prime p. So now I want to take, I will write it, I will even write it like we or in a similar way to this notation. Fpx phi is the set of all possible remainder polynomials if you do long division of a given polynomial by phi. This is, let's say, ai x to the I equals 0 up to k, where k is less or equal, well, sorry, k is strictly smaller than the degree of phi. So let's say degree of phi is equal to n. So k is strictly smaller than n, which is degree of phi. And all the AIs are elements in the field FP. Okay, this is all the possible results of doing long division with phi in the denominator. Because of course, I mean, simply take any polynomial in this set R, do long division of R by phi, and you get R. Or if you wish, you can take any polynomial in this set R, and you can add to it phi times something. Let's say phi times x, phi x times x. And then if you do long division of this expression by phi, the remainder is R. So basically any polynomial of degree less than the degree of phi can be obtained, and this is all can be obtained as a remainder in long division by phi. And on this set fpx sub phi, I define addition modulo phi and multiplication modulo phi. How do I do it? I mean, addition modulo phi is in fact just addition of polynomials. This is just add, let's say, R1 and R2 as polynomials, because if you add two polynomials, you don't increase their degree. So the addition of R1 and R2 is still a polynomial that is of degree smaller than n. But if you multiply two polynomials, the degree of the result is the sum of the degrees. And potentially, if R1 of x was of degree n minus 1, and R2 of x was of degree n minus 1 as well, then the multiplication is of degree 2n minus 2, which is already bigger than n. So you need to do modulo phi. Modulo phi, namely, you take the R3 such that R1 R times R2 is equal to Q times phi plus R3. Okay, and there is a unique polynomial R3 that is of degree smaller than the degree of phi that satisfies this equation. Okay, so we have it's like this is the analogous construction to the prime field, and now well, so what is the zero element here? I claim, let's say, theorem f p x sub phi is a field. Why is it a field? Well, the zero element is simply the zero polynomial. The constant polynomial on one is also a remainder. Let's say n is bigger than 1, then the constant polynomial is of degree less than n. Then these guys are legitimate polynomials This is, by the way, this fpx sub phi is just a fancy notation to all polynomials over fp of degree less than n. Okay, so this is associativity. What is the well, associativity is because a modulus is associative. What is the additive inverse? Additive inverse of Rx is a phi minus Rx. Phi x minus Rx, since Rx plus phi minus Rx is equal to phi x, which is equal to 0 modulo phi. Sorry. So I have an additive inverse. What about the multiplicative inverse? So here we have a lemma. If let me just pick up the notation I had. If f and phi are polynomials over f, and phi is prime, there are polynomials u and v over the same field, such that f times u plus phi times v is equal to 1. To 1 here, this is the one element in polynomials. This is the constant polynomial. And equality is equality as polynomials. Okay, so if you wish, I can write the variable fx vx plus phi x ux. Oh, I should be, I guess, u and v. So fx ux plus phi x vx is equal to 1, the polynomial constant on 1. And this lemma is another extension of the analogy between polynomials and integers. If you remember, we had the same lemma for integers. So you just replace here, you can rewrite the statement by keeping the same letters and saying, instead of these are polynomials, saying that they're integers. And we had another claim that showed that this is true for ordinary integers. Okay, so if this is true, And by the way, the proof that you have for integers, or for the integer version of this lemma, can again be pushed by the analogy, simply be translated to a proof that this lemma is for polynomials is true. This is called, by the way, the Bezout lemma. And so, using this lemma, I now want to have to show that in this field, fpx sub phi, I have a multiplicative inverse. How do I show it? So now, remember, fpx sub phi is simply the collection of all polynomials over fp of degree smaller than n, where n is the degree of phi. If Rx is some polynomial over fp, well, is some remainder polynomial, what is the inverse? Well, since phi is prime, the lemma tells me that there are polynomials u and v over fp such that Rx ux plus phi x vx is equal to 1. But this means if I now take modulo phi for the entire equation, I get that Rx ux is equal to 1 modulo phi, because when I take a long division by phi of this expression, it has no remainder. The remainder is 0. i.e., ux modulo phi is the multiplicative inverse of R. Okay, and the rest of the axioms are very easy to check. It's completely analogous to the construction of the prime field. Now, how many elements? So we before I move on, any question about the proof? I see there are. Yeah, so let's see. Multiplying a list of n elements roots will guarantee we will get a polynomial of degree n. Yeah, if you multiply x minus ai, you multiply it n times, and this is, just look at this. Let's say x minus a1, x minus a2, x minus a3. How do you open it? You need to do this times this, this times this, this times this, this times this. But really what is going to dominate the degree is you're going to have an expression x times x times x. This is the highest degree of expression that you get, so you will get x, some polynomial of degree 3. So that's for this question. Yeah, okay. Is the additive one of a polynomial? I'm not sure what this question. I don't understand the question. The additive one of a polynomial. I don't know what is additive one. Maybe additive inverse of one. Additive inverse of the polynomial, of the constant polynomial c, is minus c. So with each element that is not 0, with each element in fpx divided by prime, there will be multiplicative inverse of it. Yes, this is what we showed. This is guaranteed by the lemma. The lemma tells you that there is this u and v, and u is going to be the multiplicative inverse. By the way, I should say again the full proofs, the full details of what I say now appear in the book, like everything else. So you can always, and of course it's not the only source. You can always look there, but this is to give you some sketch of how things are constructed, and what I wanted to get to before we end this session. I mean, how many elements? What are the number of elements of FPX phi sub phi? Well, I mean, I have a polynomial of this. This is the same as, I mean, polynomials of degree less than n over the field P. A polynomial of degree less than n is completely determined by, this is the same as a vector of size n. Give me a vector of size n. Some of its coordinate may be 0, that's okay. Then I give you it determines a unique polynomial of degree less than n, right? Because a polynomial has a coefficients 0 up to n minus 1. So coefficient 0 up to n minus 1. So the number of elements in this guy is the same as the number of elements in the Cartesian product of Fp with itself n times. This is n times, which is p to the n. So you see that we have constructed, I mean, assuming you believe me that there is, you can always find a prime polynomial of degree n for any n, then we have constructed a field of size p to the n for any n. Okay, this is called the Galois field. The Galois field, this is a field of size p to the n. Observe that, well, there are several things. One is that Fp itself, is a subset, and in fact a subfield of Fp x sub phi. Why? Because I can consider Fp as constant polynomials. Okay, so Rx may be some constant C, Rx here, may be some constant C, and C can be any element in the field. So by this, I have Fp embedded into the bigger field Fpx sub phi. What is the characteristic of the new field? The characteristic of the new field is still P. Even though the number of elements is P to the n, the characteristic is still P, because you take the element 1, the element 1 here is the same as the element 1 here. You add it to itself P times, you get 0, because you add a constant polynomial 1 to itself P times. This is P times the constant polynomial, and this is 0. And the third observation is that I could have done it for any finite field. I don't need specifically Fp. I did it for convenience because you know Fp, but Fp can be replaced by any field, any finite field. Okay, and now for the big theorem. This is a classification of finite fields. For any prime p, and any integer positive integer n, there exists a field with p to the n elements, and any two such fields are isomorphic. Okay, this is a big gun. And they are denoted GF Galois field P to the N. Okay, going back to the Galois field that we kind of constructed by hand. Well, here you can take, let me just quickly Google it.
Matan, I don't mean to interrupt, but we're already 2 hours now, so
Yes, yes, I will. Okay, so and I'll just say here you can take a polynomial over f2, f. It needs to be prime polynomial. It's going to be, I think, x squared. Well, okay. You can pick a prime polynomial over f2 such that you get this addition and multiplication tables as remainder polynomials of this, but I need to check the details for the polynomial itself. So let's finish this now with just taking questions. So with so for Galois field 4, the polynomial is apparently x squared plus x plus 1. You need to check that this is a prime polynomial over f2. This is true because if you substitute 0, you get 1. If you substitute 1, you still get 1. So this polynomial doesn't have any roots. And then these guys are in fact just remainder polynomial. I mean, we call it 0, 1, 2, 3, but this is 0, 1, x, and x plus 1. And this is all the possible remainder polynomials by division of f. And if you check, you can see that the addition and multiplication tables are simply, I hope I'm not, the polynomial is correct. You can check that the addition and multiplication tables are simply addition and multiplication modulo phi is our notation. Okay, so what questions do we have? Lee, can you speak up because I don't understand exactly the question.
Yes. During your definition of the final part of the notes, you gave the definition for the Galois field, and
My question is, you wrote here, yes, scroll up a little bit. Yes, here, you give the p power to the n equal to the,
Yeah, this is
yeah, I
this
just
is
lost that
the
here.
number of elements. Yeah, okay. So we want to know. So we proved that this creature fpx sub phi, which is kind of analogous to fp, is a field. And now we want to know how many elements does it have. So I put a diez here. Okay. This so this is just, it's a question of set. How many elements in the, exist in this set? Here you don't care about what is the operation, addition, and multiplication. This set, as a set, it is simply all polynomials of degree less than n over fp, right? Yes, you follow?
Yes, 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 yes. Oh, I already got that
Okay.
part, actually. Thanks.
And how many polynomials of degree less than n are there? Well, you choose the zero coefficient. Let's say you can say a polynomial of degree less than n, is a sum, sum fi x to the I equals 0 up to n minus 1. This is a kind of a redundant notation because fi may be 0. But if for the counting, it's easier to do it this way. And so every n tuple f0 up to fn minus 1 that you choose give me a polynomial. And it's a one-to-one correspondence. How many tuples I have? N times the number of elements in the field fp.
Yes.
Is this clear, Ali?
Yeah.
Okay.
Yeah. Thanks a lot.
Any other questions? This is really a great time, I think, to tie the loose ends. Okay, so let me just quickly advertise what I want to do next time is not exactly cryptography, but rather an algorithm. This algorithm is called fast Fourier transform, and we will prove the properties of the algorithm using the stuff we did with finite fields. With I think I need a little addition to the stuff we developed. FFT is an algorithm to efficiently multiply polynomials over a finite field. So instead of doing it in complexity n square, if the degree is n for each polynomial, you can do it in n log n. And it is one of the most used algorithms in applied mathematics and especially in cryptography. So it's not a cryptographic primitive per se, but it is a very important piece for many cryptographic applications. I think it's also a great application to see the stuff we talked about in action. So that's next time. And yeah, I hope to see as many as you as possible.
Yes, we will continue next week. Thank you so much, Matan. It was really great. Awesome. Very excited to see the next talk. For now, I just want to remind everyone that we don't have a session this Wednesday. You can let us know in the Discord if you want to do special office hours in Asian times. Otherwise, we will see you again on Monday for another session with Matan, and then we'll have Tuesday, Wednesday session on the lean moved from this week. Just a reminder. Awesome. And yeah, we'll have a recording of the session with all the resources up on the Study PF Wiki tomorrow. Very well.
Bye bye.
Thank you, everyone. Bye bye. Have a great day.